So hi everyone, I'm Tzlil, and this is joint work with Aviad, who is in the audience, and also with Matt. And the topic is computing exact minimum cuts without knowing the graph. So there are some spoilers from Anna, so forgive the repetition in the introduction. The topic of the talk is this fun game. So the setting is we have an unknown graph on n vertices. We know n, but we don't know anything about any of the edges. And our goal is to compute the minimum cut in this graph using as few cut queries as possible. So our focus will be minimizing the queries, and we're allowed to use as much time as we want. Right? So what is a cut query? Well, the player specifies a subset of the nodes S. Okay, and then the oracle has to return the number of edges in the cut between S and S complement in the graph. So for example, if the player asks for the subset AB, the oracle might say that there are 4 edges crossing the cut AB, etc. Right? So the player might ask for this set, and you know that 3 edges are crossing it. For this set, 5 edges might be crossing it, etc., etc. You want to compute the minimum cut using as few queries as possible, and the whole time the oracle has to answer consistently with the actual underlying graph. So here you can see that the minimum cut is actually just separating D from the rest of the graph. Okay, so how many queries do we need to compute the minimum cut? Well, it's not that difficult to see that order n squared queries suffice to learn the whole graph. Okay, so you can learn the graph, and then you can just compute the minimum cut in the graph. So how do we do that? Well, let's say that I want to know if there's an edge between 2 vertices u and v. Okay, so let's let y be the 0, 1 indicator of whether there's an edge. And let's let x be the number of edges between u and the rest of the graph, and z be the number of edges between v and the rest of the graph. So now my claim is that I can make 3 queries. So I ask for the cut around u, the cut around v, and then the cut around both u and v. In doing this, I'll learn x plus y, x plus z, and y plus z. And from these, I can solve for y. Okay? And so having done only these 3 queries, I can decide whether there's an edge between u and v. And so if I query every singleton and every n choose 2 pairs, I'll know exactly the graph, and then I can compute the minimum cut. And it turns out that you can do even better. So if there's a graph with m edges, you can use roughly m queries. So this is better in the sparse case. And the question of learning graphs in this query model has been studied before. So this is sort of the optimal bound there. But also, it's not difficult to see that in the dense case, information theoretically, you need at least n squared over log n queries, right? And the reason that this is because the adjacency matrix of the graph contains n choose 2 bits of information. But every query that we make, we get at most log n bits of information, because we just get a number between 0 and n squared. All right, so now the question is, can we actually improve upon this to compute the minimum cut? Like, it seems intuitive that you, in order to know the minimum cut in the graph, you'd have to know the graph as well, right? And you might ask, why are we even talking about cut queries at all? Like, where's the motivation for this model? So the motivation for this model is from submodular function minimization. So I have a set of items, a set of n items, and I have a function that assigns values from the reals to every subset of these n items, okay? And I don't want to get into it too much, but we say that such a function is submodular if it has this property of diminishing returns. So this is all I'm going to say about submodular functions, but I'm also going to say that they're really important, right? So for one thing, they capture many real settings, such as maybe item valuations for bidders in an auction. Also, something that's really, really great about them is that we actually know how to optimize them efficiently, right? So I have this discrete function over an exponential size space, but actually, it's known how to minimize such a function using only polynomial and n time and queries, right? So I don't even know the value of the function on the whole set. And for a discrete function, this is actually kind of incredible. So this is a very strong property, and it's actually been studied since the 80s. So in the 80s, Grochel, I hope I'm pronouncing that correctly, Lovash and Shriver gave the first polynomial time and query algorithm. Okay, then there are many, many papers since then. But the current best record is roughly n squared queries to the oracle. Or if I'm willing to assume that the function is bounded, I can do n m cubed when the upper bound on the function value is m. All right. On the other hand, our best lower bound is only linear. So there's a specific constant out here, and then n. This is due to Harvey. And this is actually a pretty big gap, right, between n squared and n. And so the motivation of this work initially was to try and close this gap. The cut function is a submodular function. That's not very difficult to see for yourself. And as we argued a moment ago, we need n squared over log n queries to learn the graph, right? And how could you compute the minimum cut without knowing the graph? So what we were hoping is that we could look at min cut, and based on that, improve this lower bound. Okay, but as the title of this talk and also Anna's spiel at the beginning already revealed, we came across this big surprise, which is actually that in a simple graph, there's an algorithm that only requires a linear number of queries to compute the minimum cut. Okay? And even for the min st cut problem, which is a more kind of complex problem, which is still submodular, you can get subquadratic queries, so n to the 5/3. All right, and so what we can do is we can learn the minimum cut in the graph, compute the exact minimum cut in the graph without knowing the graph at all, which I think is pretty surprising. So I'll spend the rest of the talk talking about the minimum cut algorithm. As Anna said at the beginning, the algorithm is really quite simple, and maybe it's a little bit ambitious, but I think I can do the whole thing in the remaining time. So stop me if you have questions, because I'll be going fast because I'll be trying to get through all of it. Okay. So for a warm-up, so I'll prove that if the graph is sparse, right, if it only has order n edges, then I can compute the minimum cut in n log n time, or I can learn the graph in n log n time, right? So why is that? So we'll need the following lemma. Say that I have some vertex u that I'm considering. I can find a neighbor of u in only logarithmically many queries, okay? So how do I do that? So it'll be similar to the divide and conquer strategies that Cyrus mentioned in the previous talk. What I'll do is I'll randomly partition the remaining vertices into two sets of roughly equal size. Okay, I have these unknowns, the number of edges from u to v minus s, the number of edges between u and s, and the number of edges between them. And if I make these three queries, right, I learn x plus y, x plus z, and y plus z, and these suffice to learn x, y, and z, so all three of these quantities. And now, if there are any edges here at all, right, I can just recurse. I can throw away this whole part of the graph, and I can just recurse on u and s, right? Otherwise, I'll recurse on the rest of the graph, or I conclude that there just aren't any edges leaving u. Okay, and by doing this recursively a logarithmic number of times, I find one neighbor of u. This does not require sparsity. This I can do in any graph. But so actually, this gives me that if I have a graph with m edges, I only require time order m log n to learn the entire graph and then compute the minimum cut with no additional queries. Okay, so that's sort of our basic building block. It doesn't take very much to actually realize that you can bootstrap the previous routine to actually find a uniformly random edge in the graph. Okay, so what do? First, we'll take a hit of n queries initially, and we'll compute the degree of every vertex, right? Then we'll choose our special vertex u with probability proportional to its degree. Okay, and we'll randomly partition the remaining vertices. We'll learn the quantities x, y, and z. And now we recurse on the s part with probability proportional to y over x plus y. So with probability proportional to the number of edges going to s. Okay, and it's not that difficult to convince yourself if you do out the calculation that you'll actually sample every edge with uniform probability. So, and now what we could do is we could take our initial graph and we could subsample k uniformly random edges using only k log n queries, right? So this opens the door to subsampling. With only a linear number of queries, or tilde order n queries, I can take some dense graph, okay? I can subsample n log n uniformly random edges, and I end up with a sparse graph H. Okay, so you should think of this as something like independently sampling every edge with probability log n over the average degree. That's what it ends up being like. And if a cut has value c in my original graph G, then the expected value of that cut is c times p in this new graph. And so the cuts here, you might hope, approximate the value of the cuts here. So if I find the minimum cut in my subsampled graph, that might correspond to an approximate min cut in G. Okay, so you would hope that this would be true, but the problem is that if the optimum min value, if the optimum min cut has value that's much, much smaller than the average degree, right? So C star is the optimum min cut value, then the variance will be much too high. And it's really easy to see actually from this example here, right? So if I have a graph where my minimum cut is really, really small, and there's another cut that's larger than that cut, but much smaller than the average degree, then this sampling procedure won't let me distinguish between these two cuts in H. Okay, so when the average degree is much larger than the minimum cut value, we have a problem with the subsampling approach. So what we'll do is we'll reduce the average degree, okay? And in order to reduce the average degree, we'll be contracting random edges until the average degree in the graph drops far enough. So this is just Karger's algorithm for those of you who know it. Let me say a little bit more about this step. So if I knew the whole graph, right, at every step I could choose a random edge, and I could contract its endpoints into a big supernode, right, leaving multi-edges but getting rid of self-loops. Okay, and if we stop when there are some linear times the number of right, so I want it to be like a linear factor times the min cut value times n edges left, then the probability that the actual minimum cut survives is at least a constant. So this is just the sort of standard Karger's algorithm analysis, if you know it. And it doesn't take very much to realize that you can actually implement this in the query model, in our query model, relatively efficiently. So every contraction only requires us to sample a uniformly random edge, which we argued already that we could do with only logarithmically many queries, right? And the fact that we don't know any of the other edges doesn't matter because we just, simulate this supernode thing by just never separating two vertices that we know to be in a supernode. Okay, and there's the most n contraction. So this only gives us a linear number of queries. Okay, so great. So now our algorithm is as follows. We have some graph G, it may be dense. What we'll do is we'll contract random edges until we know that the average degree is like we want it, n times the size of the minimum cut value. And then we'll subsample a linear number of edges, and we'll end up with a sparse graph that approximates all of the minimum cuts well. Okay, so that's it for the approximate min cut, right? An approximate min cut in H will correspond to an approximate min cut in G. But what I promised you at the very beginning was exact minimum cuts, right? So how are we going to find the exact minimum cut? So that only requires one small idea more. So we prove the following structural lemma. So we prove that if I look at a graph, a simple graph, and I look at all of the minimum cuts of value at most a constant times the minimum cut value, which are not singleton cuts, so they're not just taking one vertex and separating it from the whole graph, then there are at most a linear number of edges in these cuts. So I can choose a linear number of edges and I can cover all of these cuts. So now I got to this point, right? I have this sparse graph that approximates the cuts in G well. What I'm going to do is, in this sparse graph, I can find all of the non-singleton cuts of size at most, that correspond to a constant factor times the minimum cut value in the original graph. Okay, now I go back here and I learn exactly all of the edges that cross those cuts, right? And now what I can do is I can just compute the min cut in that graph. And I know that I can do this because there are only a linear number of edges for me to learn because of the structural lemma. Okay, so that gives me an exact min cut algorithm that only requires a linear number of queries. All right, and then the only thing before is that I left out the possibility that it was single vertex cuts. So our whole algorithm is just we check every single vertex cut, then we guess the value of the minimum cut, right? So before I was sort of assuming that we knew what the minimum cut value was. Here we just guessed everything within a factor of 2. Factor of 2 doesn't matter. We run the whole routine as described before. And here this is only n queries to check every singleton cut. Here there are only logarithmically many iterations. And then here every step only requires a linear number of queries. So that's the min cut algorithm. All right, seems like people are with me, so that's good. It's a sign that it really is as simple as we promised. For ST-min-cut, there are a couple of complications that arise. So one problem is that subsampling is inaccurate. Okay, you can't subsample with probability proportional to the average degree. And another problem is that contracting edges doesn't preserve the min-ST cut. And another problem is that the structural lemma just stops being true, right? So there are many small obstacles. But it turns out that if you're just a little bit more careful, then you can work around these issues. So we design a more careful subsampling procedure that's similar to other works of Karger. We do our contractions a little bit more carefully in like a flow-conscious way. And we also prove a different structural lemma. And we end up still with an end to the 5/3 bound. Okay, but we conjecture that maybe end to the 3/2 is the correct bound. So that's a open problem. Some other open problems. So are there few query algorithms for the weighted graph case or the directed graph case? So in both of these cases, we don't know how to prove our result, especially because these kinds of structural lemmas that we proved aren't true anymore. For directed, it's even more challenging. We don't even know how to do subsampling. And I guess the biggest open question is, are there lower bounds for submodular function minimization that match n squared? What is the correct lower bound, or what is the correct upper bound? Maybe you could get a lower bound from weighted or directed graphs, or maybe you could get a better upper bound, which would be extremely exciting. So, okay, thank you for your attention. Yes.
Have you tried to find a Las Vegas one?
We didn't think about it, but yeah, it's definitely a Monte Carlo algorithm. Yeah, there's some probability that you don't up with the right answer. Yeah.
So weighted graph is submodular for positive non-negative weights?
Yes.
In negative weights, means the modularity.
I believe so. Yeah.
Okay, let's take all this together.